presentation around.
This is being recorded.
Yeah, I will try to make my presentation with 40 to 45 minutes, and I will leave about 10-15 minutes to take the questions from you guys. Okay. And today my topic is directed hybrid random networks mixing preferential attachment with the uniform attachment mechanisms. And this is a joint work with Dr. Tiandong Wang from Texas A&M University from the United States. And the paper has been accepted for publication on the Annual South Institute of Statistical Mathematics. And I'll get started. So my presentation will be divided in the following several sections. I will give some introduction at the beginning, and I will propose our model, present some theoretical results, followed by simulations and applications to real data, and I will carry out a bunch of discussions at the very end. So let me start with the introduction. Okay, so first of all, let's take a quick look at the PA rule. PA stands for preferential attachment. So preferential attachment refers to a network evolution mechanism where the probability that a node is sampled at a renewal point is proportional to its degree in the present network. So it looks like a little bit long definition. So let me give a mathematical definition of it. I know you all like math, and let's take a quick look at it. So if we have a network G, which consists of a vertex set V and an edge set E, and the probability that a node I is sampled under the so-called PA rule, preferential attachment rule, is given by Di out of the sum of J in V of DJs. So I mean, where the Di is the degree of I. And so this what this tells us. So I mean, in a given network, suppose that we have a node with high degrees, a large number of degrees, which means it has a large number of edges connected to it, then it will come with a high probability to be sampled to recruit the newcomers for the growth of the network. So this is the PA rule. So that's why we say it is proportional. The probability that the node is sampled is proportional to its degree. And this is the mathematical definition of that. And the PA, preferential attachment, has been a very popular mechanism for modeling real network data. So I gave a couple of examples over here. And back to very early 1965, and the Solar Price, and he used this PA rule to model a citation network. And later on, Merton studied the Matthews effect in 1968, and this is also very much related to preferential attachment. So what is Matthews effect? It's very much like a economic manifestation. So it is something like the rich gets richer, the poor gets poorer. And a little bit recently, Mark Newman from University of Michigan, he used the PA rule to model collaboration networks. Like that's a collaboration between the scholars in the field of physics in the United States. So why PA networks are very popular? Because it has a very great feature, which is called scale-free. So if you are not familiar with scale-free means like the degree distribution of the network. It follows a power law. So that's why PA-based networks are very popular for modeling real network data. There's another thing, because my model will be mixing PA rule and UA rule, where UA stands for uniform attachment. So let me give a quick, definition for UA, and this is very simple. So uniform attachment refers to a network evolution mechanism where all the existing nodes are equally likely to be sampled. So let's go back to that, mathematical definition. Suppose that we have a bunch of nodes in a network, then the probability of sampling an arbitrary node indexed with this I is 1 out of the cardinality of V. So the cardinality of the set V means all the number of nodes that we have. So suppose we have 5 nodes in total, and each of nodes under the UA rule will be the probability that it will be sampled will be 1 out of 5. So this is just uniform, kind of like a uniform attachment. So UA-based networks, we do not really, it doesn't really have too many applications to real network, fit, because it is too simple to fit any real network data these days. However, in the past, I have seen UA-based networks which were used to model disease spread and growth of computer networks. And specifically, when I say that I have seen these models, they are very much coming from something called the random recursive trees. And there are a bunch of, random recursive tree papers back in the 1980s and early 1990s. And my advisor at the George Washington University, Professor Hossam Mahmoud, he is one of the experts studying random recursive trees in that period. And of course, I mean, recently I have seen paper which has extended the model from classical UA-based networks. And I give one example here is the random exponential recursive trees. That is also authored by Professor Hossam Mahmoud, and it was published on the probability, MCAP. So it's a methodology and computing applied probability. It has been published in 2021. So here are the basic informations. What are the motivations of carrying out this research? What we have found through the very rich literatures and the existing papers, we have found that even though PA networks, they have very good property of scale-free, however, they do not always fit the real network data well due to the complexity and heterogeneity in the network data. And sometimes they are not able to precisely capture some key attributes of the real network data. So let me make it a little bit simple. So what is the biggest problem of PA rule for fitting the real data? We know that the degree distributions of PA networks, preferential attachment networks, they are scale-free. They are following power law. So they are having very heavy tails. However, in practice, based on some social network data that we have seen from the existing repositories, and we do see that even those tail distributions, tail degree distributions, they are heavy, but not that heavy, which were captured by PA networks. So we would like to find some, more powerful and models which would give, something like power law. However, the tail distributions are not that heavy. This is the main motivation of this study. So one of the primary reasons is that degree distributions of some real network data are not very heavy as the power law that we have seen. So there are a bunch of studies that have considered alleviate the heaviness of the tail degree distributions. And one of the pioneering work was conducted by Cooper and Alan Fries in 2003, and they proposed a mixed model for web graphs. Even though they didn't specify it was a mixture of PA rule and UA rule, however, after we deeply investigated their paper, it was actually a mixture of PA and UA rule. And a little bit recently, Xiao and his colleagues conducted a simulation study of degree distributions in a mixed network model, where they found that, oh yeah, the degree distribution in a mixed network model still has some heavy tail features. However, the tails are not as heavy as pure PA rules. But they were doing a simulation study. So it was more like an empirical study. And Atlee and his colleagues proposed a mixed model for the buyer-supplier network in the United States. So they are economists. They try to use this idea to study the buyer-supplier network, and it was more like an application paper. And more recently in 2019, and Medina and her colleagues introduced an EM, expectation maximization algorithm, for the parameter estimation for a mixed network model. So all these, papers in the literature have shown that a mixture of PA and UA rule probably would give us, some better insights of the real network data. So this motivates us to, generate our study. And we are considering a network, a class of networks called a hybrid random network. And hybrid just can be thought of as an integration of PA and UA rule. And we can extend it from some existing work. We are considering a directed network in our study. So our network, HRN, standing for hybrid random network, is governed by a bunch of parameters over here. And the HN, the subscript N, that is referring to time. And the Vn and the En, they are just the vertex set and the edge set at time n. So I will give a more specific explanation of these parameters over here: alpha, beta, gamma, P, delta in, and delta out. So alpha, it is the probability of a directed edge from the newcomer to an existing node. Gamma is the probability of a directed edge from an existing node to the newcomer. Since I said that we are considering a directed network, even though it is a edge connecting a new node and an existing node, we have to specify two different scenarios by accounting for its direction. And the beta is also a probability, but it is complement of alpha and gamma. It is the probability of a directed edge added between two existing nodes. So our model is a little bit different from the pure growing model. So we are really considering some kind of scenario such that we do not really have newcomers joining into the network at any renewal points. There could be a chance such that there is an edge emerging between the existing nodes. And the P is something that of primary interest. It is the probability of executing PA rule. So I mean, because we are considering a mixture of PA and UA rule, so P specifies the probability of implementing PA rule, and then in what follows, 1 minus P would be the probability of implementing UA rule. And the delta in and the delta out, they are the, we can think of they are the tuning parameters which control the growth rate of in and out degrees. I have a small graph over here to help you better understand it. So we actually, in this model, we are considering 3 different scenarios. And the first scenario, as I mentioned, that is a newcomer giving an edge to an existing node. So the first graph over here is corresponding to the alpha scenario. And the rightmost one is corresponding to the gamma scenario, because it is a directed edge from an existing node to the newcomer. So in alpha and gamma scenarios, we always have a newcomer joining. However, the only difference is the direction. And the beta, that is the middle one. It is an edge between the 2 existing nodes from the network. There will be no newcomer joining the network. Because of this, actually, this makes our model a little bit more challenging to analyze, because keep this in mind, we do not always have a newcomer joining the network, which means the total number of nodes in our model is not a fixed value. It is random. Sometimes we do have newcomers, sometimes we do not. And this would cause the main technical issues in giving technical issues for giving the theoretical results. So this is the general picture of our model. And let's take a look at each of the scenarios. I will give a more detailed explanation of one of the scenarios, and the rest will be, will be very similar. So we consider Jn, which is an indicator telling us the occurrence of the scenario. So if Jn is equal to 1, that means scenario 1 will be implemented. That's the occurrence of scenario type alpha at time n. So at this point, as I mentioned, at this point we are going to add a new node u, and it will give an edge to an existing node I. So that is the scenario of adding node u to the network, connecting it to an existing node I by a directed edge. And I is belonging to the existing network. So what is its probability? Okay, let's take a look at it. So because P is the probability of implementing PA rule, right? Okay, so we have probability of P that will implement PA rule, and 1 minus P that will implement what? UA rule. So the latter part is easier to understand. That will be 1 minus P times 1 over the cardinality of Vn minus 1, because we have Vn minus 1 number of nodes in the network. So 1 minus P times it, that's the part of UA rule. How about the PA rule? Let's take a look at the small figure over here again. Let's see. It's a directed edge from the new node to the existing node. The new node, we don't really have nothing to sample because that's a newcomer. However, for the existing node, I over here, it will, if this edge is added, the in degree of I will be increasing by 1. Therefore, our model is considering, okay, suppose your I, the node I here, has larger in degrees, then it will have a higher probability to be sampled. That's why we will have the degree of I at the time n minus 1, and we have a small superscript in overside refers to its in degree. And so the numerator will be the degree of I, the in degree of I at time n minus 1. That's the definition of this guy. And we have this plus delta in, that is the tuning parameter. It tells us the growth rate. It is a parameter that we have given at the very beginning. So what will be the denominator look like? Denominator just taking the sum of all the edges, all the nodes in Vn minus 1. That's the vertex set. So the denominator is just taking the sum of all the in degrees of the nodes in the network, and each of them is a plus a delta in. And this is the so-called PA rule. So it will be multiplied by P, because this P specifies the probability of executing PA rule. So this is the model, this is the explanation of the alpha scenario. And let's move to beta. It looks a lot, actually, it's not that bad. So we are having Jn equals 2 over here. That means the beta scenario. Beta scenario is what? That is an edge from connecting two existing nodes. So we suppose we consider it as I and J. They are the two existing nodes, and the I and the J, they are sampled independently. Okay, let's go back to this diagram a little bit. We can see it's an out of J to in of I. So we would think, suppose the J has a larger out degree, it will have a high probability to be sampled. And if I has a large in degree, and it will have a high probability to be sampled. Therefore, we have this. J, we're considering out. The formula looks really similar to the previous one. So it will be P of implementing PA, Y minus P, probability of implementing UA for J. The top one is for J because we are considering the out. That's why the subscript over here is J. And the bottom one is for I. So it is because it's a direct edge from J to I. So we have P probability of implementing PA rule and Y minus P probability of implementing UA rule. Of course, I know some of you guys, you are really good mathematicians. You have seen some, okay, we probably can simplify it a little bit. That's correct. We are going to simplify it later, but now I'm just giving this more complex formula to illustrate our idea. And the last one is scenario 3 gamma. That's a new edge, the edge from an existing node to a newcomer. So I'm not going to repeat myself because this one has become very obvious to us. Now, yeah, as I mentioned, we're able to do some simplification because we have observed the denominator here can be simplified in the following way. Because anytime as we are adding a new edge to the network, the total in degree and the total out degree, it is always increased by 1. It doesn't really matter which one is which, but the total increase is fixed. And therefore, we are able to simplify the denominators for the first component over here. We are able to simplify the denominator of the first 2 components over here, as well as the denominator over here, by using these, by observing these 2 relations. So as I mentioned, the main challenge is that this one appears in the denominator, and it contains a term of Vn minus 1, which is the number of nodes at the time n minus 1. Suppose this one is a fixed value. It is not random. Then this problem will be much easier because we are able to use a very standard recurrence method to get whatever we want. However, as long as we are considering the beta scenario and we have to have some random Vn minus 1 cardinality in the denominator, this very small change actually makes the theoretical development very challenging. All right, let me show you some. This is the introduction of the model. Let me show you some theoretical results that we have found. First, we have mainly focused on 2 things. One is the degree growth of a fixed node. So we kind of like define 2 constants, C1 and C2 over here. They are the functions of alpha, beta, P, delta in, and delta out. And what we have derived is that for fixed node I, there exists random variables. This is Xi, this is zeta I and Xi, such that as n goes to infinity, and its in degree and the out degree after properly scaled converge almost surely to those 2 finite random variables. So we are not able to determine the distribution of these 2 random variables. We are only able to prove the existence of these 2 random variables at this moment. And I'm not going to bother you with very much detailed proof, that I will show you like the basic ideas that we implement. So the sketch of the proof, actually, it is not that complicated. So what we are doing is, based on the relation that we are having over here, we have this relation, right? So we know the full, evolutions mechanism. Then what we can do is to create 2 sub-martingale sequences based on di in and di out. After having these sub-martingale sequences, we apply the martingale convergence theorem to establish the sub-martingales, and then we are able to get the existence of the existing results over here. So the main idea is to develop the martingale sequences for di in, the in degree sequence, and out degree sequence respectively. And after having that ready, and we apply the martingale convergence theorem. And this martingale convergence theorem is extended from Dub's martingale convergence theorem. And we will refer the interested readers to Rick Duret's textbook in 2006. And it is theorem 4.2.11. So it is like a little bit more, direct application. And this tells us that what? This tells us what? This tells us that the degree of a fixed node I and the in degree of a fixed node I and out degree of the fixed node I, while they are, properly scaled, and as n go to infinity, they almost surely converge to their respective random variables. And we show the existence of the convergence. The second property that we spend a lot more time on are the degree counts. Sometimes we also some statisticians and the researchers like to call it as degree distribution. So what we are doing here is the following. So we are kind of like define two new trade-off, or we say tuning parameters, delta tilde in and delta tilde out. They are the functions of delta in, p, and beta. And delta out tilde is also a function of delta out, p, and beta. And we define these two things. And we also kind of like defined four independent negative binomial random variables. Their parameters are given by each of these combinations. And we also consider two, exponential random variables, which are independent from those four negative binomial random variables. And these two exponential random variables, they are given by the rates of these two things over here, these two big formulas over here. And these are kind of like the definitions. So what we want to study are the following. So I have this nm in n and nm out n. Let me tell you what does it mean. Nm in n is defined as the number of nodes of in degree m at time n. So it is counting the number of nodes of in degree m. M for Mary, m Mary. And this n out m of n is the number of nodes of outer degree m at the time n. And what we show the following. So we say if they are scaled, each of them is scaled by p, scaled by n, each of them converges in probability to some known random variables. They are respectively denoted by phi tilde in m and phi tilde m out. And their definitions are given on the next page. So it is like a combination of two negative. Each of them is a combination of two negative binomials. They look very symmetric, just like we are telling that, okay, these two random variables, degree counts, they converge in probability to two random variables. And we know what these two random variables look like. They are just too long, and I don't really even require you saying, oh, just memorize what we have done here. But I mean, I'm just telling you that what we are interested here is we are interested in the degree distribution. We are interested in the degree counts, the in degree counts and out degree counts as n goes to infinity. And what's the probability of in degree count or out degree count is equal to n. And these are the general properties of interest in random network studies. And the sketch of the proof. So this one is a little bit more complicated than the previous one, because the previous one is just an application of martingale convergence theorem. Here we need to do a little bit more. So first of all, we are proving the concentration of these two random variables. Take the in-degree count as an example. The out-degree count, it is done very similarly. So we first show that the in-degree counts as n goes to infinity, it is around its expectation. This is in some textbooks, this is called focusing results. And this focusing results actually was, I think, first studied by Cooper and Alan Fries in another paper. They did a lot of work on these focusing results. And our strategy is to utilize the proposition 8.4 from Van der Hofstede textbook. And this idea was mainly developed by Dijven and the colleagues very recently. So what we do, actually, how to show this focusing results? Actually, the general framework is very straightforward. So we are establishing a new sequence, ZT. And this ZT actually is a martingale. This is a martingale sequence. And we kind of like convert the focusing result, what we are interested in. So we want to show that this guy minus its expectation is, the probability it is greater than some very small value is very small. So I mean, we want to say that, okay, this value and this value, they are very close to each other as n goes to infinity. Then we only have to focus on this expectation. So our strategy is to establish a martingale sequence for that. And we only focus on this martingale sequence, and then we are able to apply the Azuma-Hofting inequality, because Azuma-Hofting inequality is designed for martingale sequences. So we kind of like translate the target into a martingale structure and apply the Azuma-Hofting inequality to that to get the focus result. After having this focusing result, what is the good benefit of that? After having this one, we only need to focus on this expectation part. And we have some known results derived by Dr. Tiandong Wang and her advisor, Dr. Sidney Resnick. They consider something called linear birth process with immigration for embedding such structure. And they use the known results from branching processes to give us the results. So I mean, this is the general idea of that, and it probably will take me 20 hours to illustrate every single details. However, I would like to give you, a little bit more room to, kind of like show you the basic idea behind it, and you can check out paper or Dr. Wang and Dr. Resnick's paper about the details of implementing this strategy. And this is the example of doing in-degree counts, and we can show the results for out-degree counts in a similar manner. But even though I would let you, explore it by yourself a little bit, but I would like to give a few more words about linear birth process with immigration. What does that mean? I think this is a very good strategy. It can be applied to a large number of different network models. So basic idea is the following. We know if we have a pure birth process, then what we are having is we have a lifetime parameter, lambda, which is usually greater than 0, right? And if that's a birth process without considering immigration, it actually is a continuous Markov process with transition rate Qi from state I to state I plus 1. It is linear, lambda I. Now, oh, I'm sorry, this is a typo here. So if we consider a delta, immigration parameter delta over here, then we would plus the delta over here. So this should not be eta, this should be a delta. So instead of considering a linear relation directly, we are just adding one, constant term, which is called immigration parameter delta. This should be delta. Sorry about that. So this is just like an extended, pure burst process. So let me take an indirect PA as an example. So what we can, how to embed it? The fundamental idea is each node I, it is endowed with an independent, burst process with immigration, BI. And it comes with the transition rate. And it is like J plus delta. Because lambda here, it will be equal to 1. Because this J can be thought of as a degree of the state J. So, and the delta is the immigration parameter over here. Then, tau Ki, it records the jump times of the BI process. So tau Ki, if you can think it of like, okay, like when every node comes with a clock. And when the clock rings, it will be selected and to attach, right? So it is kind of like clock. When it rings, it will be selected and attached. So tau I is the time of this clock rings. So in the jargon of stochastic processes, it is the jump time. It's when it is selected. And after the sampling is done, and all the BIs, they are restarted. And then this is the basic idea of embedding the indirect PA network into this burst process with immigration. And now, if we are considering direct PA models, as we are doing in our paper, we, instead of having one BI process, we just want to compare a pair of BI processes, respectively, for in and out degrees. This strategy is very, needy, and it's very helpful and very convenient for us to get some very complicated results. Think about it. We are really developing something which is a combination of two negative binomials. Without those properties and without the existing results from these linear processes, it's very difficult to find this negative binomial and find these rates. Because of these known results from the both the burst processes, we're able to get what we want to do. And I would like to guide you to this paper, Wang and Resnick, 2020, for more details. The paper, to the best of my knowledge, it recently has been accepted for publication on advances in applied probability. But it's still in press. It's not ready yet. Okay. Now, after having everything ready, we are able to write out the log likelihood. Theta is the collection of all the parameters, including alpha, beta, gamma, delta in, delta out, and so on. And this boldface E is the record of all the edge evolution process. So we are able to write out this log likelihood. So what we want to do is we want to do the estimation. What I mean estimation is giving me a network, and what can we learn from this network? Can we estimate alpha, beta, gamma, delta in, delta out? And what is the most importantly over here is our P, the trade-off parameter, the balance parameter of executing PA rule and UA rule. Estimation procedure. So we are considering two possibilities of doing such estimation. First of all, we can treat the log likelihood, this very big chunk of formula, as our objective function. And we can apply the nailed-mead algorithm to solve a nonlinear optimization problem. So we want to optimize that log likelihood function. And we want to get something like maximum likelihood estimators for the alpha, beta, gamma, and so on. This method is very good, and it's very helpful in a lot of scenarios, and it is very, very fast. It probably can solve the problem within 2-3 seconds. However, this method has a big shortcoming of being sensitive to the selection of initial values, which means it is an optimization problem. So we have to give some initial values to tell them where shall we start. Suppose the initial values are far away from true values, this algorithm usually fails. So we are looking for an alternative. We are considering the Metropolis-Hastings algorithm in a Bayesian framework. So this is the MCMC technique. And this method, it is more robust. It always gives the results. However, it takes a much longer time to get the results because MCMC based algorithm, they are known for slow. So we are thinking possibly we are able to integrate these two methods and to get what we want. And while we were submitting the paper for publication, the referee came back to us about the model identifiability issue. And I would like to address here that our model is good when P is strictly less than 1. If P is equal to 1, it is a pure PA model. And it will be difficult to distinguish our model and the pure PA model. So, but as long as P is something less than 1, say 0.999999, even that close to 1, our model will be working fine. Simulations. So we focus on the comparison between the nailed-mead and the Metropolis-Hastings algorithms. We're considering the P, 3 different values of P respectively corresponding to dominant PA, roughly even P and UA and dominant P UA. And we are also considering different combinations of alpha beta with large alpha, large beta, or small beta but equal alpha and equal beta, equal gamma. Our delta in and the delta out, they are just we just select these 2 values pretty randomly based on our previous studies on some social network data. We do not really consider very large simulation runs. We set it at 100. And in our simulations, we set the size of the networks at 10 to the 4th. Because we are doing Metropolis-Hastings, so we have a Brownian number and we do it at 10 to the 4th. And the size of the Metropolis-Hastings is 2 times, it's like 20,000. And here are some simulation results. As we can see, even though I'm just giving you those percentage of bias over here, these values look a little bit big. Actually, they are doing fine. I just want to let you know the estimation of delta in and the delta out is an unsolved problem. Our estimates are not that good because keep this in mind. Delta in is 1.3, delta out is 0.7. Our estimates, they are just okay. They are not really very well. But our estimates of P hat, the P, are pretty good via both methods. We do not really see severe bias over here. When P is getting a little bit smaller, and we can see that, okay, actually the nailed-mead method gives more accurate, estimates, and the standard errors are relatively smaller than the Metropolis-Hastings. And when P is even smaller, and taking value 0.2, nailed-mead is pretty, pretty doing well, and the P for Metropolis-Hastings, sometimes it has larger percentage of bias, but they are still okay. They are on the line. It's acceptable. So what is our conclusion? Nailed-mead, it seems doing well than Metropolis-Hastings. However, what I didn't really write out here is that out of 100 simulation runs, only 70 to 80% of the nailed-mead algorithm will work. So these results are not really based on 100 simulation runs. It is based on like 70, 80, results. But Metropolis-Hastings always work, even though it doesn't perform as well as nailed-mead. That's why we considered an integration of these 2 methods. For example, if we have some auxiliary variable about the knowledge of P, delta in, delta hat, delta in, delta out, then let's do nailed-mead because it performs better. If not, why don't we try Metropolis-Hastings algorithm at the beginning to get better initial values? Then we apply to nailed-mead. That's what I call the integration. applications. So we have applied our data to two different, real network data, and I'm going to present one over here. So I'm going to present one, our applications to a regional network of Facebook users in New Orleans in Louisiana from September 2004 to January 2009. This data is open to everybody. It is available on Connect, and this is a website that you can just click on it, and it will guide you to the data repository. The network is directed but unweighted, which is our case. So each directed edge from I to J means user I writes a post on user J's Facebook web page. We didn't really consider the full network for two reasons. First of all, it is enormously large. It's super large. And there are several studies carried out by researchers found that the data before 2006, it is not very stable. So we select a subnetwork from January 2006 to the end of June of 2006. It contains a total of 4,200 users, and the number of edges is 11,422. But we have to modify our network a little bit more to study this model. We are considering two additional scenarios, 4 and 5. So in the past, just let me remind you a little bit more. In the past, we are considering 3 scenarios. Alpha scenario, new node giving an edge to an existing node. Gamma scenario, existing node gives an edge to a new node. Beta scenario, an edge is added between 2 existing nodes. After carefully reviewing the data that we are having here, we have to have 2 new scenarios. Scenario 4, we specify it by parameter Cassie. It is like a new edge. It is a new node. It gives a self loop to itself. So it's just, this one is very weird. Like, I'm a newcomer joining this network, and I write a post on my own web page. Is it possible? Possibly. What we have observed this scenario, so we have to add one more. Scenario 5, 2 nodes joining into the network together, and there is a directed edge connecting them. So adding these 2 scenarios actually is not that bad. We just have to add 2 more into this log likelihood function. So it's not too bad. It's just, some additional computation work. Doable. And in the paper that we have submitted for publication, we have another web, network data that we are analyzing. That's the Dutch Wikipedia talk data. It is also available on Connect. So we applied the Metropolis Hastings algorithm to this network data, and we know this is MCMC algorithm, and we use some graphical tools to check the convergence of the estimation of the estimating results. And these red lines, they are the empirical, they are the they are the averages, and we can see that okay, excuse me, these red lines are the estimates that we get based on our method, and we have seen that okay, our results, our estimates, they are around these true values, which shows the convergence of the Metropolis Hastings algorithm, because we do not really have analytical tools to check the convergence. So we're using these graphical tools. So because you remember, we have a Bergin number, we have a size, and we take the very large several values, and we just plot it over here and compare with the estimates that we have. And we have seen they are all doing fine, except this delta in. It seems that our estimates is a little bit underestimating the true parameter, but they are kind of like on the line, acceptable, probably. And our our main competing method is pure PA model, not really considering the integration of UA and PA mechanisms. So the black dots over here, it gives us the tail distributions of they are the empirical tail distributions. And we have the estimates for our HRN, the hybrid random network model, and the estimates for not using the hybrid structure. We just we estimate the results via the PA network model, and we generate 50 independent HRNs and PAs, and we plot their tail distributions to see whether or not they are well covering the true tail, the empirical, the true tail structure of the in and out degree distributions. And we can see for our case, I mean, we are doing fine on the out degree, not that well on the in degree, but both of them are doing better than their counterparts by applying the PA model directly, which doesn't consider the integration of uniform attachment. Therefore, we concluded that our method does have an advantage of, like, I will not say advantage. Our method, at least for this particular data set, outperforms the standard preferential attachment model, but it still has room to get improved. So in the last of a few minutes, I'm going to carry out a few discussions. So as I said, we do have the room to improve. First of all, we have seen that the estimation of delta in and the delta out is not really good enough. And if we go with the MC-based algorithm, the computation efficiency is an issue. It's not very fast. And the models itself may have some improvements because we are now only considering directed networks. We do not really consider any weights. After considering weights, it will become very, very much more complicated. In addition to that, at each stage, we are adding one new node to the network. Possibly this is not the fact. A more realistic model will be we are adding a random number of nodes. It could be based on some distribution like Poisson. Suppose we don't really have a fixed addition, but a random addition. Are we able to develop something from there? It is also a question. Lastly, now we are more like studying a snapshot of a network. And suppose we are considering a more complicated spatial and temporal setting on the network, and it will be more challenging. And we are really thinking, okay, now what we want to do is to alleviate the heaviness of the tail distributions of in degrees and out degrees. So, I mean, is that the only option? Are we able to enhance the goodness of fit of a random network model? Not just, changing the model itself, by looking into some other crucial, network model properties, such as assortativity. It captures the correlation structure between different nodes and different nodes features, clustering coefficient, or some other topological indices. They can be some alternatives that we can always think about. And the main challenges from our point of view is theoretical results for very complex network models are always not easy to get. The more complexity it is, the harder for us to get the theoretical results. So maybe more studies will be based on empirical studies. And we need some improvements and some, more methodological improvements to get our new theories, especially asymptotic theories. Next one, heterogeneity in real network data. So one of our conjectures is that, we are not doing very well while we are estimating delta in and delta out. One possible reason is the reciprocity. So we have reciprocal edges. What does that mean? So for example, I see Professor Mahmoud is here. Okay, I write a post on Professor Mahmoud's webpage, and probably he will reply me immediately or within a short time of period. This reply may not follow PA rule or UA rule. It may be just because I wrote a post on his webpage, so he replies. So they can be forming a group of reciprocal edges. They are neither captured by PA rule or UA rule. So how can we model these things in the study that could improve the estimation performance of the network models? And we have a recent paper just accepted for publication on statistics and computing. That's the one that we have proposed the DIDPR, which is the a direct network degree preserving algorithm for considering the associativity correlation structure in PA network models. If you are interested, you can take a look at it. And finally, I would like to give some acknowledgements and special thanks to my collaborator, Dr. Tiandong Wang from Texas A&M. And the paper has been accepted for publication on the Annals of the Institute of Statistical Mathematics. And if you want to print, it's in press. It may take a while. We know Springer is not very fast. So if you are interested in the paper, please feel free to ask me for a copy, or you can just go to archive and you can search this title, and we do have an archive version over here. And thank you very much for your attention. I know I'm running a little bit late, but please feel free to ask any questions, or if you have more details that you want to discuss, please feel free to shoot me an email. Thank you again for your attention, please. Oh, by the way, I'm just going to the very last page for some references while any of you are asking any questions.
Okay, thank you, Panpan, for this nice talk. If is there any question in the audience, please?
Please go ahead.
So, if you need some enlightenment or details, please go ahead. I see that Dr. Hussam Mahmoud joined us.
Yeah, I do see him. He just turned the camera on. The camera off.
Yes, I'm here. Hello, everyone. I'm here.
Glad to see you. How's they going? Yeah. Thank you for coming. And I mean, if you don't really have any question at the moment, feel free to email me over here if you want to ask later.
Okay. Thank you so much for the nice talk.
Thank you very much for your attention, and thank you very much for your time. Appreciate it. And thank you again for the cordial invitation from Rafiq, even though I don't really see Rafiq, which is
No, I had a problem. He has to travel 2 days ago to Tunisia.
Okay.
No, it's not a big problem, but he had to travel without. He didn't plan to travel this period, but he had to.
Okay. Hopefully everything is going well.
No, it's doing.
All right, cool.
Thank you.
Thank you.
Thank you again.
Bye.
Yeah. Enjoy the rest of the day, guys. Bye. Take care.
Thank you very much.
Thank you.